we will be discussing altitude correction, then calculation of amplitude and azimuth, little bit about longitude correction, and familiarization with the almanac. So that's the plan for today. So we will just refresh the altitude correction, and then we will go into the almanac and see from where we can pick up all these corrections. So I would recommend बेटा कि आप almanac जो है ये अपने पास रख लो, 1992 almanac. If it is far off, you can just keep it close to you. Just keep your calculators and almanac and notebooks with you. So we will be able to proceed ahead. Okay, so I hope all your almanacs are with you. So let's continue. Now, अभी तक हमने बेटा दो सेलिंग्स की हैं, प्लेन एंड पैरेलल सेलिंग and Mercator sailing. So these sailings, as I told you, are different methods with which we can calculate courses and distances between any two positions on the Earth's surface. Now that is the primary job of the navigator. You have to take your ship from position A to position B. So the first thing which the navigator requires to make the passage plan are the courses and the distances. So ये courses और distances दोनों हमें मिलते हैं sailing methods के साथ. So we have done two of them, plane and parallel sailing and Mercator sailing. Later on, going forward in the coming months, we will also be doing great circle sailing and composite sailing. So these are other two forms of sailing which are there. So we will be doing them also. Now, once you have calculated courses and distances, the next job of the navigator is to monitor the progress of the ship on the planned passage. So you have initially calculated courses and distances, you have made the passage plan. After the passage plan is made, the ship starts to proceed on that passage plan. So our next job is to monitor our progress. Now, how do we monitor our progress? Nowadays, it is very easy. You have a GPS satellite navigation position fixing system which is available to you. So it gives you every position, new position every second. You get this live position on the axis and everything goes on smoothly. Now, what we are going to do in navigation henceforth, यहाँ से आगे जो हम navigation में करने वाले हैं, these are, for today's date, these are basically the emergency navigation techniques. So we will consider that GPS is not there. Satellite position fixing is not there. Okay. When you depart from a port, for some time you will have the land-based navigational aids, terrestrial nav aids available to you. You will have lighthouses, buoys, beacons, beacons, features of the coastline. All these will be there to help you fix your position. You can get position lines, position circles, and you can plot them on the chart and fix up your position. But once you move into the open sea, all these shore-based or land-based or terrestrial navigational aids are going to go outside your range of visibility. So there, the only option which is available to us is celestial position fixing. So all these celestial bodies, what are these celestial bodies? The bodies which we see in the sky. Okay, these are basically, they can be categorized into four types of bodies. The most prominent one is the sun. Then you have the moon. Then you have the planets. And then you have the stars. So four different categories of celestial bodies. All these celestial bodies can act as lighthouses and they can provide us with position lines. Something very similar to, you take the bearing of a lighthouse and you have a PL on the chart. Something very similar to that. If you can observe a celestial body, it will immediately give you one position line. So that is our ultimate aim. All these things which we are going to do now will basically lead to fixing our position. So step by step, we will keep on doing that. I will tell you what are the steps involved. Now, the basic thing which we need to calculate a PL using a celestial body is its altitude. Okay, what we need is the true altitude of the body. What is this altitude? Altitude is basically a concept in navigation which is based on celestial sphere. Okay. What I will do is I will send you a few links, YouTube videos, so you can watch those videos at your convenience. That will give you an idea of the celestial sphere. So for now, I will not go deep into it because right now our emphasis is on practically calculating our position. Okay. Later on, when we go into the concepts, then I will cover this concept of celestial sphere also with you. So this true altitude, what is this true altitude? Just to give you a very basic concept. The celestial sphere is a imaginary sphere. Okay, it's an imaginary sphere. And to specify a sphere, you need to have two things known to you. One, where is its center? And second, what is its radius? Now, the center of the celestial sphere is the same as the center of the Earth. So, Earth and celestial spheres are both concentric spheres, and the radius of the celestial sphere is infinite. So, if you have a sphere with the center same as the center of Earth and infinite radius, that is assumed as a celestial sphere. All the celestial bodies are assumed to be on that celestial sphere. Practically, it is not so. Practically, which is the closest body to us, beta? Celestial body?
Planets.
Moon.
Moon, sir.
Moon.
Very good. So you have the moon, then comes either the planets or the sun, one of these two, depending upon where the position of the planet is in its orbit. So you have the planets and the sun, and then going further, you have the stars. So practically, you see, in reality, they are at different distances from us. We have already reached up to the moon. We have our footprint in the moon. We have reached up to some of the planets. Some of the planets we have sent our rovers. So sun and stars are still not explored yet. So they are at different distances from Earth. But as far as our navigation calculation is considered, we consider all these bodies to be situated on the celestial sphere itself. This makes the calculation using these celestial bodies very, very easy for us. So we have the celestial sphere. Now on this celestial sphere, we have some special reference points. What are these reference points? If you imagine a line from the center of Earth passing from the observer's position and going up to the celestial sphere, that will go up to a point which is directly overhead of you. Directly overhead of you. What do we call that point, beta?
Zenith.
Very good. That point is called as zenith of the observer. And a point exactly opposite to it, reciprocal to it, which will be on the other side of the earth. It will be below our feet on the other side of the earth. That is known as nadir. So zenith and nadir are two reference points which we have on the celestial sphere. And exactly midway between them, we have a great circle. What do we call that great circle? Exactly midway between zenith and the nadir.
Rational horizon.
So that is the rational horizon. That is what we call as the rational horizon. Okay. So when you talk of the true altitude of a body, the true altitude basically tells us how much above the rational horizon a particular body is. Okay. So we have the zenith exactly on top. We have the nadir reciprocal to the zenith on the other side of the earth. Exactly midway between them, we have the rational horizon. It's a great circle. Very similar to like on earth, we have the poles. Exactly midway between them, we have the equator. So something similar to that on the celestial sphere. And if you join the zenith and nadir with great circles, there can be infinite number of great circles which can pass through them. These are called as vertical circles. Vertical circles. So the definition of the true altitude is, it is the arc of the vertical circle contained between the rational horizon and the center of the celestial body. That is what true altitude is. Now, if we want to obtain a PL, we need to get the true altitude of a body. The instrument which we have to obtain the true altitude is the sextant. Sextant is an instrument which can help us in measuring angle. We use the sextant in chart work also, in horizontal sextant angle, in vertical sextant angle. So sextant as an instrument is available to us for taking the altitude of a body. But the problem is, the altitude which we obtain from the sextant is known as the sextant altitude. It is not the true altitude of the body. Why is it so? See, the true altitude, as I just now told you, is the arc of the vertical circle contained between the rational horizon and the center of the body. It can also be defined as angle at the center of the earth contained between the plane of rational horizon and the line joining the center with the center of the body, center of earth with the center of the body. So true altitude should be measured at the center of the earth. Okay, and it is the angle between the center of the body and the rational horizon. Now, when we use the sextant, the problem is we cannot go up to the center of the earth. We are using the sextant at the surface of the earth. So this angle which the sextant is measuring is the angle at the eye of the observer. The angle what we require is the angle at the center of the earth. So this is the difference between the sextant altitude and the true altitude. The second difference is, sextant can measure an angle between any two things which are visible to you. Now we can see the celestial body, that's all right, but we cannot see the rational horizon. The horizon which is visible to us when you are on the bridge looking at the horizon which is visible to us is called as visible horizon. So the altitude of the sextant is referenced to visible horizon. The true altitude which we require is referenced to rational horizon. So this is the difference between both of them. And we have to convert this sextant altitude to the true altitude. Now, how do we convert it? We can convert it by applying some correction. We have done these corrections in second mates also. We have done these corrections in pre-C also. Now, I will show you the corrections. First, you tell me, you want me to go into the basics of the corrections also, or shall we go to the correction calculation straight away? So,
सर थोड़ा बेसिक बता देना सर.
Okay, ठीक है बेटा, मैं basic भी, I will touch the basic slightly. Being here is the center of the earth as well as the center of the celestial sphere. ये जो छोटा sphere आप देख रहे हो, the smaller one, this is the earth, and the big sphere which you are seeing, that means basically this sphere which you are seeing is the celestial sphere. Now, if you join a line from the center of the earth passing from the observer's position, you see the observer's position is indicated by O here. So if you draw a line joining the center with the observer's position and you extend it upwards, you reach up to the zenith. So this Z point here is the zenith of the observer. Now this dotted line which you are seeing passing from the center of the earth is the rational horizon. This is the rational horizon. We have the observer at the center of the earth somewhere here, and the observer is actually watching a body. This X which I have shown here, this is a celestial body which the observer is watching. So if you want to identify the true altitude in this diagram, let me show you with a different color. I told you the true altitude is the arc of the vertical circle. This is the arc of the vertical circle contained between the center of the body, so it should go up to the center, and the rational horizon, or the angle at the center of the arc contained between the center of the body and the rational horizon. So you see this angle is shown here as the true altitude. Okay, this is the true altitude of the body. This is what we require to calculate our position line. Now the angle which we obtained from the sextant, what angle do we obtain from the sextant? See, the observer's eye is at point E. You can see point E here. This is where the observer's eye is. Now when the observer sees the body, this is the line of sight. And the observer sees the visible horizon. The visible horizon is a horizon on the Earth's surface. See this dotted line which you are seeing here, VV dash, this is the visible horizon. So this line shows where the visible horizon is, and the angle between them is what we can measure using a sextant. Now when you use a sextant is a very sensitive and delicate equipment. So it can have error of its own. It has many moving parts, a sliding arm. There are two mirrors which are movable. So there is a telescope. So all these moving parts, it can have error of its own. This error is known as index error. Okay. So index error is denoted as either on the arc or off the arc. So whenever we get any angle from the sextant, the first correction which we need to apply is the index error. So you can see here on the left hand side, we get the sextant altitude of a body. The first correction which we apply is the index error. As far as our MMD questions are concerned, this index error will be provided to you. They will tell you this much is the index error of the sextant, and they will also tell you whether the index error is on the arc or off the arc. Now, how do you apply it? Very simple technique. Remember this trick, that consider the index error as a switch. If it is on, you put it off. And if it is off, you put it on. Okay. So what do I mean by this? If the index error is on, you put it off. Off means negative or minus. And if the index error is off, you put it on. On means positive or plus. So that is how we apply the index error. Once you apply the index error, the altitude which we obtain is known as the observed altitude. So you see here, this red color angle which I have made here is the observed altitude of the body. So we reach up to the observed altitude. Now the next correction which we apply here is, you can see this is the rational horizon here. This dotted line passing from the center of the arc, this is the rational horizon. And you can also see this VV dash is the visible horizon. These are the two horizons which I have shown you. Now there is a third horizon also which we consider in these problems. The third horizon is known as sensible horizon. Okay? Sensible horizon. What is this sensible horizon? Sensible horizon is basically a plane which is passing from the observer's eye and which is parallel to the rational horizon. So something which is parallel to rational horizon and passing from the observer's eye. Let me highlight it using green color. This plane which you see, it represents the sensible horizon. So this green color plane which we see is the sensible horizon. So when we correct the altitude, what we do is, first of all, we convert the horizon from visible horizon to sensible horizon. Okay. So how do we do that? We do that using dip correction. Okay. So let me first tell you the concept, then we will go to dip correction. See, we know the true altitude of the body is here at the center of the earth. This is the true altitude. And we also know that rational horizon and sensible horizon are parallel to each other. Now, if I join a line from center of the earth to the celestial body, CX, this line, this will cut the sensible horizon at point S, and there is a geometry theorem principle which says that if you cut the parallel lines by a third line, it will cut them at the same angle. So if this angle XCH is our true altitude, then angle XSA, okay, let me mark it with some other color. The yellow color or the orange color angle which I have made, both these angles, the green angle and the yellow angle, should be same. So which means this is our true altitude. Now this yellow angle, if you see, is the exterior angle of triangle XES. Let me mark this triangle. This is the triangle I'm talking about, XES. The yellow angle which we want to find out is the exterior angle of this triangle. Now, geometry says exterior angle of a triangle should be equal to the sum of interior opposite angles. So what are these two opposite angles? Let's mark them. Two opposite angles are, one angle is here, the blue color angle, and the second angle is, let's change the color. Let's pick up dark green. So you can see two internal angles of the triangle. One is the green color angle, another is the blue color angle. Now this green color angle which we see, what angle is this? This is basically the angle at the center of the celestial body subtended by the radius of the earth. And this angle is known as parallax angle. This is the definition for parallax. This angle is known as parallax angle. And the blue color angle which we see here, how can we obtain this blue color angle? We have our observed altitude which goes up to visible horizon. Now somehow if we are able to find, let me highlight this angle. If we are able to find this red color angle here, which is basically the angle between the sensible horizon and the visible horizon, this angle I'm talking about. If we are able to find out this angle, you subtract it from the observed altitude and you can get the blue color angle. So the angle between visible horizon and the sensible horizon is known as dip angle. So what we do is, after we have the observed altitude, we apply the dip angle to it. It is known as dip correction. And you can see from here that this dip angle or the dip correction will always be negative. How big or how small this angle is, it is decided by the height of eye of the observer. The more is the height of eye, the more is going to be the dip of the horizon. This is also known as dip of the sea horizon. So more the height of eye, more will be the dip angle. So from the observed altitude, we subtract this dip angle and we obtain the blue color angle. This blue color angle, which is the interior angle of our triangle XES, is known as apparent altitude. So you can see here also, once we apply the dip correction, we reach up to the apparent altitude. Now to this apparent altitude, if we add the parallax angle, green color angle, we can get the true altitude. So parallax is added. Okay, you can see here I have written parallax is always positive, it is always added. Now up to here is okay, but there are two more issues which we need to resolve. What are these two issues? One is the refraction of the atmosphere. What is this refraction of the atmosphere? Now we are able to see any celestial body because of the light either being emitted by that body or reflected by that body. Like all the stars are visible to us because they emit light. There is a combustion which is going within the stars. So because of that combustion, light is produced. That light reaches to us, and that's how we are able to see them. We are able to see the moon and the planets because they reflect the light which they are receiving from the sun. So when light from a celestial body reaches to our eye, that is how we watch or we see that body. Now, when this light passes through the atmosphere, it undergoes refraction. What is refraction? Refraction is a phenomena in physics which says that whenever a ray of light travels from two different mediums having different densities, the ray of light will either bend towards the normal or away from the normal. So let me erase the ink and show you reflection now. If you are receiving the light from a celestial body, let's say you are here and you are receiving the light from this direction, the light is coming to you like this. The body will appear to be here. This is where the body appears to be, but actually the body is not here. Where is the body actually? The actual body is somewhere here. What is happening is the light from the body is coming in this particular direction. Once it passes through different layers of atmosphere, it undergoes refraction. If you want to show the normal, this is the normal here. And since the density of the atmosphere is more than the density of space, the ray of light bends towards the normal. So there is a bending in this particular fashion, and it appears to come from this direction. So all the celestial bodies, because of refraction, appear higher than where they actually are. So whenever we see a body, the altitude what we obtain is slightly more than the actual altitude of the body. So if you want to get the actual altitude, you have to subtract this refraction. So you see here, after the apparent altitude on the left side, we have the refraction, and this correction is always negative. So this is the refraction correction which we need to apply. Now the last issue which remains is, if you are observing a body which is not a point object, say for example, sun and the moon, these two objects are not point objects. They appear like disks. Now, when an object is appearing as a disk, you are not able to identify its center. We cannot see the center of the disk. So when we are taking the altitude, we can either take the altitude of the lower edge of the body or of the upper edge of the body. Now in navigation, we call this as lower limb or upper limb. So if you are taking the altitude of sun and moon, and if you have taken a lower limb altitude or upper limb altitude, to reach up to the center of the body, you will have to add or subtract the radius of the body, or you can say the semi-diameter of the body. Radius and semi-diameter, they both mean the same thing. If you observe the lower limb, you have to add the semi-diameter, and if you observe the upper limb, you have to subtract the semi-diameter. So on the left side, you see this correction here, semi-diameter. In case of upper limb, it is minus, and in case of lower limb, it is plus. So this is a summary of all the corrections which we have. Now let me show these corrections to you one by one once again. Any doubts which you have in this diagram, beta? Okay, so let's see what we have discussed till now. What we obtain from the sextant is the sextant altitude. The first correction which we apply is the index error. If it is on, we put it off, means it will be negative. If it is off, we put it on, means it will be positive. Once you apply the index error, we get the observed altitude. To the observed altitude, we apply the dip correction. Dip correction is based on height of eye of the observer, and this dip correction is always negative. Once you apply the dip correction, you get the apparent altitude of the body. To this apparent altitude, we apply three different corrections. The first one is refraction, which is always negative. The second one is semi-diameter. In case of lower limb, it will be positive. In case of upper limb, it will be negative. And the third is parallax, which is always positive. And once you apply these three, you get the true altitude of the body. Now, in second mates in pre-C, you applied these corrections separately also. But in phase 1 level, usually they will never ask you to apply these corrections separately because it is considered much below your level. So we apply these three corrections, that is refraction, semi-diameter, and parallax, all together in one single correction, and we call that the total correction. We obtain the total correction from the almanac straight away, and we apply it, and all these three corrections are taken care of. Okay, so up to here, any doubts, beta? Very good. Let's proceed further, and let's now see how are we going to get these corrections. Again, as I told you, index error is provided to you in the question itself. They will tell you whether it is on or off. So you will just pick up the value from there and you will apply it. After that comes the dip correction. Dip correction is obtained from the almanac. So if you have the almanacs with you, you can just open up. I'm going to familiarize you with the almanac now. Though it is done in second mates, you have used it extensively, you have familiarized yourself with the almanac in pre-C, but I'm still going to do it so that there are no doubts in your mind. Okay, so I'm going up to the bare basics and covering up everything. So dip correction, just open up the first page of your almanac. On the first page of your almanac, on the right hand side part, you will see the dip correction table. So you have the height of eye given here, the height of eye is mentioned, and along with the height of eye, you have the correction also mentioned. Okay, so there is a single correction for a range of height of eye, like for example, you can see from 14.2 to 14.7, the correction is minus 6.7. That is the dip correction. So that's the first table which we have, the dip correction table. Now, after the dip correction, you will obtain the apparent altitude. The next correction which we require is the total correction. So let's see the total correction now. Again, on the first page itself, you will find the total correction for the sun, stars, and planets. इन तीनों की total correction आपको first page पे मिलेगी. The first table which you see is the total correction table for the sun. I highlighted it with a red band. Now this total correction table is divided into two parts for six months of the year, October to March and April to September. So depending upon when are you taking your sight, you enter into that particular part of the table. In each part, you see two corrections given. One is for the lower limb, other one is for the upper limb. So you just check in the question, which limb have they used for the observation? Basis that, you pick up the correction from here. You will see all the corrections under the lower limb are positive corrections. You have to add them. And all the corrections under upper limb are negative corrections. So you have to subtract them. That's for the sun. For the stars and planet, you go to the next table. This gives you the total correction table for stars as well as planets. You enter into these tables with apparent altitude and you can obtain the correction from here. All the corrections for stars and planets are negative corrections. Okay. Now, when you are picking up the correction for planets, be careful when you are picking up it for Venus and Mars. There are total 4 planets which we use for celestial navigation: Venus, Mars, Jupiter, and Saturn. Now, out of these 4, Venus and Mars, they are the inferior planets. Venus is the inferior planet, Mars is the exterior planet. They are closer to us as compared to Jupiter and Saturn. So, when you are using Venus and Mars, with the total correction which you pick up from the table, that is this part, you have to apply a additional correction also. A extra correction also has to be applied. So where do you get this extra correction? You will see along with this normal correction, you will have a additional correction also given. This is the additional correction which is given. Okay. It will look slightly different on your almanac because you will be using 1992. This one is 2009. So these corrections change from year to year. So how to apply this additional correction? You check up the date on which the site is taken. And as per that date, you see if there is any correction applicable. Like from January 1 to January 28 and May 23 to July 10, if the altitude of Venus is between 0 and 41, the additional correction is plus 0.2. If the altitude is between 41 to 76, it is plus 0.1. If the altitude is more than 76, there is no correction given. So no correction is required more than 76 altitude. Okay. So as I told you, this additional correction table will differ from year to year. The one which I am showing you is 2009. The one which we use in the MMD is the 1992 almanac. Okay. Now, important thing to remember here is that when you are applying the total correction for Venus and Mars, remember that this additional correction is additional to the normal correction. Okay, normal correction तो लगेगी ही लगेगी, additional correction उसके साथ extra लगेगी. Don't forget to apply the normal correction. Okay, so beta, this is also clear to everyone, the total correction for stars and planets and sun.
Yes, sir.
Very good. Let's go to the moon now, the last celestial body which we have. Now, in case of moon, the table is given on the last page of the almanac. So on the last page of almanac, you will see the moon total correction table. This table is divided into 2 parts. So you can see this is the upper part of the table. This is the lower part of the table. Both these parts, they give us 2 different corrections. So let us go into these parts one by one. If you zoom into the upper part, this is how the upper part looks like. We enter into the upper part of the table with the apparent altitude. You see, we enter with apparent altitude. Let us say, for example, the apparent altitude of the moon is, let us say, 32 degrees and 30 minutes. So you see 30 to 34 altitude here. For 32 degrees, if you enter into this column, 30, 31, 32, and the minutes are 30 minutes. So with 32, you see 00 minute, 10 minute, 20 minute, 30 minute. So for 30 to 30, the value is 57.8. That is the first correction. It is known as the main correction. So this is the first correction for altitude correction of moon, the main correction. So in this case, it is plus 57.8 minutes. Okay, now let's go to the bottom part. How do you enter into the bottom part? whichever column you entered from the top, you go into that same column in the bottom part also. So in the bottom part, you go into the same column. Now, when you enter in this column, you see U and L. These are upper limb and lower limb. So you check in your question whether they have taken the altitude of the upper limb. If so, you enter under U. If they have taken the altitude of the lower limb, you enter under L. Now, where do you have to stop? Now, the rho is decided by the HP of the moon. What is HP? HP is the horizontal parallax. What is horizontal parallax? I told you about parallax in the diagram. It is the angle at the center of the body subtended by the radius of the earth. Now, if you measure that angle when the body is horizontal, or you can say the body is on your sensible horizon, it is in the same plane as the eye level of the observer. That time, if you measure the parallax of the body, it is the maximum parallax which the body can attain. So that is known as the horizontal parallax. So you have to enter into this bottom part with HP or horizontal parallax of the moon. How do you obtain the horizontal parallax? For that, if you go into the daily page, let me open up a daily page here. You can see this is a daily page of the moon. Now in the daily page, you see with the date along with every hour, you have the HP of the moon mentioned. Okay, so HP of the moon is mentioned for every hour. So just pick up the value from here. Let's say, for example, 59.7, and you enter into the table. So when you enter into the bottom part, enter with 59.7. So you see 59.7 here. You can see the two values given here, 7.2 if it is a lower limb observation, and 4.8 if it is a upper limb observation. So this is how you obtain the second correction. This is known as HP correction. So main correction from the top part, HP correction from the bottom part. Both these corrections are positive. Both are positive. So you add both these corrections. If it was the lower limb observation, once you add these two, the altitude is corrected. You get the true altitude. But if this was an upper limb observation, then you can see in the notes mentioned here, for upper limb observation, 30 minutes is to be subtracted from the altitude. So after these two corrections are done, you can subtract these 30 minutes and you will obtain the true altitude of the moon. So beta, moon table also refreshed in your mind. Any doubts you have in this table, you can ask me.
सर ये हॉरिजॉन्टल पैरेलैक्स का प्लीज एक बार दोबारा बता देंगे.
ओके, तो बॉटम पार्ट में जब हमने एंटर करना है, वी हैव टू एंटर विद हॉरिजॉन्टल पैरेलैक्स. The row has to be decided by what is the horizontal parallax of the moon. So how do we obtain the horizontal parallax? Open up any daily page or date page on your almanac. कोई भी एक पेज खोल लो बेटा, डेट वाला, any page. If you open up the date page, like see, this is March 7, 8 and 9, you will see under the moon column. Under the moon column, you will have a separate column for HP of the moon. So HP of the moon is picked up from here and is used to enter the bottom part of the total correction table.
यस, एंड फाइनली इस करेक्शन को अपर लिम्ब होगी तो सब्ट्रैक्ट कर देना है. लोअर लिम्ब के लिए क्या बोला था सर आपने?
Okay beta, I'll repeat again. So HP is clear beta. You pick up the HP from daily page.
Yes sir, yes sir.
You go back to the table. तो इस टेबल में हम HP के साथ एंटर करेंगे. Let us say, just tell me, I'll give you an example. Whether have you taken upper limb or lower limb observation, beta? Just pick up one, any one.
Lower limb, sir.
Okay, so it's a lower limb observation. Let's say the HP we have obtained from the almanac is 59.7. This we have obtained from the daily page. So let us say the altitude was 32 degrees. So when we enter into this column, we see the HP equal to 59.7. This is where we have that HP. Now we see there are two values given, 7.2 and 4.8. Which value we will pick up? It is a lower limb observation. So we pick up the value under L. The value is 7.2. So this is our HP correction. The HP correction is always positive. Okay. Main correction and HP correction both are always positive. There is no negative here in this entire table. No negative. All are positive corrections. So
Okay,
you
sir.
add the main correction as well as the HP correction, and the altitude is corrected.
Yes,
Okay,
sir.
beta. Lower limb clear?
Yes, sir. Yes, sir.
Now let's assume that this was a upper limb observation. What would we do then? Then we have to enter under U. Okay. So again, 59.7 under U, you have the correction as 4.8. So we will apply this correction as 4.8. This is plus. As I told you, all the corrections, irrespective of whether it is upper limb or lower limb, all are plus. So you add this 4.8. Now,
Yes, sir.
once you have done that, once you have applied the main correction as well as the HP correction, both are positive, both are added up. After that, you just read this note given on the right hand side. It says 30 minutes is to be subtracted from the altitude of the upper limb. So after adding both these, just do minus 30 minutes. Okay.
This only has to be done in case of upper limb. That's it.
That's right, beta. This is only in case of upper limb.
Okay, sir.
Okay.
Got it.
Okay, beta. So that is a proceed further. Chronometer time ambiguity, date ambiguity, and all this small stuff we will see.